Hello guys, welcome to my video. So today I'm going to be solving the October-November 2016 paper 1-2 for physics, and the question paper is 1 hour 15 minutes long, and I'm going to be explaining some of the questions and how they can be answered. So I really encourage you that you stick along so that you can be able to see how some of these questions can be really answered. But if you have a specific question that you really want to be tackled, or a particular question that you want to be addressed, I'd highly recommend that you use the timestamps. You can go in my description below and you'll see different times and different questions that I've solved. So if you have a particular question that you want to be solved, you can just go there and click on that question. Or you can even skip on my particular video. You see the questions outlined, so you can be able to go to that particular question that you really want to solve, okay? That you really want to be solved, okay? So please like that you really want to be solved. So please like, comment, share and subscribe, and hit that notification bell button. Okay, so let's begin. Let's start with question 1. We'll be given concrete with a density of 2,400, right? So we've been asked which mass of concrete fills a space of dimensions 8 times 10, 8 times 90 centimeters times 110. Okay, so basically we know that density is basically mass divided by volume. Okay, so if I want to find the mass, okay, it's going basically to be the density multiplied by the volume. But what is my density? It's 2,400, okay, multiplied by my volume, which is 8 over 100, multiplied by my other volume, which is 90 over 100, multiplied by my other volume, which is 110 over 100, right? If you compute that, that's going to give you an answer of 190 kgs, which is B. So very important, right? Density is mass per unit volume, and you can then be able to find your mass. Okay. For question number 2, the speed v of sound in a gas is given by that equation, where P is the pressure and rho is the density and Y is a constant. What are the SI base units of Y? So the question with SI base units, it will always be the same. Make that SI base unit the subject of formula. That's the first step. So if we were to make it the subject of formula, so for question 2, if we were to make that the subject of formula, it would be V squared is actually gamma multiplied by P divided by rho, right? So the units of that would actually be V squared multiplied by rho divided by my pressure P. But the units of V is actually ms to the power of negative 1 squared multiplied by the value of rho, which is kg, m to the power of negative 3 divided by kg, m to the power of negative 1, and s to the power of negative 2. Okay, so if we're going to cancel this out, so this cancels out with that. S to the power of negative 2, that's also s to the power of negative 2, that cancels with that. That's m squared, m to the power of negative 1, that's going to be m squared, that's going to be m to the power of negative 1, which is m to the power of negative 1, divided by m to the power of negative 1. Those two cancel out, that's going to be equal to 1. Okay, so since it's equivalent to 1, it means that, you get it, there are no units, right? So since there are no units, we're going to say our answer is D. Means that is homogeneous. The left hand side is equal to the right hand side without including the units of that constant. Okay, very important. Question 3, the motion of a moving object from rest, right? From rest means that u is equal to 0, with constant acceleration a may be represented by the equation as shown, which rho describes the quantities represented by the symbol v and s, right? So basically from v squared is equivalent to u squared plus 2as. This is going to be 0. So we're left with v squared is actually 2as, right? So v is actually the velocity. But what kind of velocity is the final velocity? A is actually the acceleration, okay, which is constant, right? And s is basically the displacement, okay? So s is basically the displacement, right? And we know that velocity is a vector, okay? Acceleration is a vector, displacement is a vector, so it's going to be vector and vector, and the answer is going to be D. Very important. I'll move to question number 4. We'll be given a cathode ray oscilloscope which displays a waveform. The time interval between two adjacent peaks is going to be that 0.006, okay? And you've been asked to find the time-based setting of the cathode ray oscilloscope. So question 4 is basically a cathode ray oscilloscope question. For a cathode ray oscilloscope question, we basically know that the period is going to be equivalent to the number of divisions, okay, the number of divisions multiplied by the time-based setting. So if you want to find, you guessed it, if you want to find the time-based setting, it's going to be your period divided by the number of divisions. What is your period? It's 0.006. How many divisions do you have? From here, let's start over here. This is the middle point of here, right? So this is going to be 1, that is going to be 2, that is going to be 3. So it's basically divided by 3. That's going to give you 0.002, right? But this is actually 2 times 10 to the power of negative 6. That is not true. This is 20 times 10 to the power of negative 6. That is not true. This is 2 times 10 to the power of negative 3, which is 0.002. So the answer is C, because that answer is actually aligning with that. That is 3. It's not even anywhere close to our time-based setting. So the answer is C. Okay. Moving on to question number 5, we've been given the value for the acceleration of free fall on Earth. So you're on Earth, and the value of free fall, the acceleration, is going to be 10. Which statement is correct? So basically, the value of A actually on the Earth, so the value of G is actually 9.81 meters per second. But for some instant, you're measuring with an instrument that only has 1 unit, right? It has no decimal places. So if you round 9.81, it's basically going to give you 10, right? To 1 SF is going to give you 10 meters per second. Isn't this answer 10? And isn't this also 10? What does it mean? It means that it is accurate. Okay, it is accurate, but that makes C and D wrong. But it's plus or minus 2, meaning that it can exist from 8 up until 10. If you draw this as a graph, it's more like this, right? This is about 8. That is about, sorry, from 8 to 12 rather. From 8 to 12, right? That is 10. That's about 12, right? More like that. It's existing over from all that 8 to 12. That is where you expect to find that value of G. But that's not really precise. Why? Because the precision of a value of G is actually 2 dp, 9.81. But here we have 10. It is not at all precise, but it is very accurate because it's actually close to the true value of G. Moving to question number 6. We've been asked to determine the atmospheric pressure rho, where rho is actually rho GH, and we've given these quantities themselves, and we've been asked to find the value of P with its uncertainty when stated to an appropriate number of significant figures. What do they mean, an appropriate number of significant figures? I'm going to explain how that is so. Is actually H rho G. Okay, so the value of H is 0.762. Is it in meters? It is. Okay, multiplied by the value of rho, which is 18,600 kgs m to the power of negative 3. That's true. Multiplied by the value of G, which is 9.81 meters per second, right? So everything is in their correct SI base units, right? So if I'm to calculate this, I'm presumably going to get an answer of 101,662.992 pascals. Basically about 1.016 times 66 times 10 to the power of 5 pascals, right? So this is my value of atmospheric pressure. But how do I find the uncertainty? The uncertainty would therefore be, okay, get this, it will be delta P, which usually be equivalent to delta rho, okay, delta rho over rho, plus delta G, okay, plus delta G over G, plus delta H over H, multiplied by the value of rho. So basically you're going to say, okay, 100, right, since this is 100, divided by 13,600, plus the value of G, 0.02 divided by 9.81, plus the value of H, right? The value of H is 0.05005 divided by 0.762. And if we're all going to compute all that, multiplied by 1.01166 times 10 to the power of 5 pascals, that's going to give you an answer roughly of 1,621.866. Okay, but get this, this is actually 0.1, right? This is 0.1621 times 10 to the power of 5. And the rule is, they said appropriate number of significant figures because the rule is the number of significant figures in your uncertainty, get this guys, should always be 1. It's a rule. It should always be 1 sig fig. Okay, so if this is expressed in one significant figure, this would be 0.2 times 10 to the power 5. But this value, basically this value gets the number of decimal places that are in the uncertainty. So if I have an uncertainty of 0.02, sorry, this is 0.02, right? Sorry. This is 0.02, not 0.12, right? So this is 0.02, right? So 0.02. Okay, so if you're going to get 0.02, this value should follow suit. It must also have the same number of decimal places. Let's start with A. This is 0.016. Remember, this should be 1 SF. This should be 1 SF. This is percentage. Why are we even putting percentages over there, right? It doesn't make sense. So the answer has to be D. Why D? 2 SF, 2 SF. 2 decimal places, 2 decimal places. One significant figure, that the value of P, we don't even care about the significant figures. What should have one significant figure always is the value of your uncertainty. Very important. I'll move on to question number 7. A lorry travels at a constant speed. Okay, constant speed. So basically, before we attempt this question, I can already see distance and time. So I will assume that the gradient of a distance time graph tells me something about speed. That's going to be my assumption, right? So I'm told that it's traveling at a constant speed. So what do I expect? I expect a constant gradient, right? Then it decelerates until it stops. Deceleration means what? My gradient is decreasing until it stops. Stops means velocity 0, distance is not changing. Let's start with A. Is this initially constant? No, because it's starting at 0, right? So it can't be A. Move to B. This seems pretty straight, right? So this seems pretty constant. We have a decrease over here, okay? A decrease over here, yeah, meaning a decrease in velocity, sure. The velocity is now 0, or the object is now stagnant, right? It's not moving, yeah, pretty much B, right? Constant velocity, constant speed decelerates, then it stops, right? It can't be C because it's starting with 0, right? It doesn't make sense. It can't be D. Yeah, it's starting with that, okay? Right, with that constant velocity, but it's negative, right? It's a constant speed, sure. And if you look at D, the value of the distance is usually going out to be 0, right? It doesn't make sense that you say that the distance that you travel is going to be 0. You have traveled a certain distance, right? So that distance, you're stopping at that particular distance. It's not going to change. If it's 2 meters that you've traveled so far, it's going to change. But this is, you're starting at a very high distance that you're moving backwards. It doesn't make sense, right? Very important. Moving to question 8. We'll be given the vertical velocity of a parachutist during the first 20 seconds of her jump, and we've been asked approximately how far she falls before opening the parachute. You need to know this. The area of a velocity time graph represents what? It represents the displacement, right? That's very important. It represents the displacement. So how do you find the displacement? Is the area underneath this graph, okay? But before she opens the parachute, she'll open the parachute approximately over here. This is where I basically approximately think that she's going to open her parachute. Again, this is very subjective. 1, 2, 3, 4, 5, right? But the beauty of this is that, look at this, how different these answers are. You might get 560, 540, you might get 390, 380, you might get 720, but they will lie within that range, right? The tricky part is 710 and 770, right? We have to be very careful about that. But basically, if I go down here, right, over here, this is essentially going to be a trapezium, right? This area over here, right, is going to be a trapezium, right? So how do I find the area of a trapezium? That's pretty simple. The area of a trapezium is going to be 1/2 base plus A, or not base specifically, but it's just one value of B and one value of A, and this is the value of your H, right? So it's half B for A multiplied by H, right? So this is, let's see, 1, 2, 3, 4, 5, approximately 5. Okay, so it's half of 5 plus this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right? So basically 14, and this height is 60. And that's going to give you an answer of 570, or 570 exactly, right? Which will be B. So you approximate the area underneath the graph is the displacement, and approximately find the area underneath that graph. Very important. Question 9. A girl is jumping on a trampoline, which graph shows the variation of the girl's velocity with time t. So let's assume the girl starts at a very high velocity, which is very true here. The girl started at a very high velocity. Like on a trampoline, what's going to happen is, you can see over there, As the girl falls on the trampoline, they're going to start with a velocity that will be very high. So velocity here will be high. But as they fall down, the velocity is going to be 0. Then they're going to start moving up. The velocity is going to increase until the velocity is high again. It reaches a high value, then the velocity is going to what? Going to decrease until it reaches 0. Reach another high value. So that will keep on happening, right? So it's going to start at the maximum value. Let's start with B. It's going to start at maximum value, but it's going to increase linearly. Right? It's not going to, it can't be B and it can't be C. But with B, it's assuming that my acceleration is constantly changing. It doesn't make sense. Both the acceleration here is different. The gradient just keeps on changing, right? It can't even be C. C doesn't make sense, right? There's squares at the bottom. It doesn't make sense, right? But let's look at A and D and specifically explain why D is correct, right? So let's look at D. It's going to start at a very high velocity, like we said, and it's going to decrease until it reaches 0. Why does it reach 0? When the girl reaches the trampoline, and it's going to increase in the opposite direction, okay? Increase in the opposite direction, and then the child or the woman is going to reach the highest point on the trampoline, right? And immediately, as they reach that highest point, right, it's now going to be, let's say for 10 meters per second, it's now going to be 10 meters per second going down, right? It's now 10 meters per second. Automatically, it has to change and start being 10 meters per second going down, right? Then they start again. They fall, which is 0 when they reach the ground or when they reach the trampoline, increases in the opposite direction as they go up. They reach the top, it changes direction automatically, it becomes positive. They start again, they fall down, so it becomes D. It can't be A, it doesn't make sense. If they reach 0, right, they go down. This is not instantaneous, this is too much, right? Because that is almost instantaneous. Immediately, they just change the direction, they start facing down and they start having a negative value, they start going down, right? So the answer has to be D. Very important. Question number 10. In order that a train can stop safely, so you want to stop a train safely, it will always pass a signal that shows a yellow light before it reaches a signal that shows a red light. Drivers apply a brake at the yellow light, and this results in a uniform deceleration to stop exactly at the red light. So guys, again, draw diagrams, illustrate this so that you can be able to understand what's going on. So if I were to draw a diagram here, okay, this is my diagram, right? And this is the yellow light, as you can see over there. That is the red light, as you can see over there. And when they arrive at the red light, the velocity must be 0, right? The final velocity must be 0. The distance between the red light and the yellow light is actually x. So this distance, okay, this distance is actually x. The speed of the train is increased by 20%, meaning if it was 100%, initially, is now going to be 120% because we've increased by 20%. If you had 5, if you increase by 20%, it's 20% of 5, then you increase by 5, right? Or you can just say 120% times 5. You have already increased it, accumulating that particular value, okay? But we haven't changed the deceleration of the train. What will be the minimum distance between the lights? So we've increased the speed. What will be the minimum distance between the lights without necessarily changing that? So what would be the minimum distance between the red light and the yellow light that will be there? Because the driver is applying a brake at the yellow light, and this results in a uniform deceleration as they stop at the red light. So get this. Since this is the red light and that is the yellow light, we're going to solve it simultaneously. The first equation, v squared, is actually u squared minus 2as, minus because it's a deceleration. The final velocity is going to be 0. So 0 is actually going to be u squared minus 2as. So 2as is going to be u squared. So u squared is going to be 2ax. X, because that's the difference initially. So this is case 1. Okay, moving on to case 2. We've increased it. We still have v squared is u squared minus 2as. We still expect the initial velocity to be u, but this time, right, we still expect this to be 0. Okay, again, we also expect this to be 0, right? So it's going to be 0. Okay, but this time was changing this value of u. It's going to be 120%, which is 100 over 100, 120 over 100 times u, all of that squared, minus 2as. So that's going to be 0, is actually equivalent to 1.2 u, all of that squared, minus 2as. So 2as, right? So in that case, 2as is going to be 1.44 u squared. But guys, we've already said that u squared from this relationship, right? We've already said that u squared is 2as. So it's just a matter of us taking this value and substituting it over there. Okay, I hope you're following. So it means that 2as would therefore be 1.44 multiplied by 2ax. If I divide both sides by 2a, so 2a over here and 2a over there, they cancel out. I'll be left with the value of s being 1.44 multiplied by x. So it's 1.44 multiplied by x. So very important for you to be thinking of that. So yeah, it was a little bit complicated, but you just have to apply the principles. First, create a simultaneous equation and solve it with the other equation that will be there. Question 11. Two frictionless trolleys are moving towards each other along the same horizontal straight line. Their masses and velocities are as shown. The trolleys stick together, so they coalesce, they stick together. What is the velocity of the trolleys after collision? So how does this work? Basically, with momentum, it's going to be momentum before should be equal to momentum after. Okay, momentum after. So before, what's going on here? Before we have 2 times 1. So before we have 2 times 1, but it's subtract because this is acting in the negative direction and this is acting in the positive direction. So subtract 4 multiplied by 3, right? This should be equal to momentum after the collision, right? So I hope you're following. That will be equal to the momentum that will be after the collision. So this will be 2, subtract 12, that's going to be 10, is going to be equivalent to. But after the collision, what's going to happen? They're going to stick together. So if you're going to remove this particular force, so let's remove it. Okay, they're going to stick together. So how is it going to work, right? So they're going to form one body because they have stuck together, right? And this has mass 3 kgs and that has mass 2 kg. And then now both, instead of moving with 4 meters per second, right, that goes away, they're now going to move with one velocity. So they're now going to move forward with one velocity v. And that's the velocity that we want to find. So I know this is negative, right? So the mass that I have is going to be 5, right? 5. So that's 10. So the mass that I have is going to be 5 multiplied by v. So the value of v is going to be 10 over 5, which is going to be 2 meters per second. Why did it coalesce and move in that direction? It can't move in the opposite direction to the right because it doesn't make sense, really, to be honest. The smaller mass has a smaller mass, smaller velocity. How can it push the bigger one and actually cause it to move in the opposite direction? It's like you have a truck and a car, they have an accident and you expect the car to push the lorry. It won't make sense. The truck will just override and just crush the car and they'll both move forward together. Okay, so the answer is going to be A. Very important. And with question number 12, we're given a bullet of mass 8 grams. Okay, traveling at a speed of 300 meters per second. The bullet hits the target and stops after a time of 100 microseconds. What is the average force exerted by the bullet, by the target on the bullet? So question 12. Okay, so very important. Okay, with question 12, we know that the resultant force is going to be the change in momentum, okay? The change in momentum divided by the time that has been taken, okay? So my momentum was once 300, right? So it's 300 multiplied by the mass, because remember, momentum is m delta v, right? That's basically how we find momentum. So 300 multiplied by 8.0 divided by 1000, right? What is my time? It's 100 microseconds, which is 100 times 10 to the power of negative 6. Roughly, that's going to give me about 24,000, right? 24,000 newtons, which is D. So just think about this. Change in momentum divided by the time you take, and that would be the answer. Very important. But for question 13, a light bulb is falling vertically through the air. Okay, so if this light bulb, okay, as you can see over there, and it's falling down vertically through the air. So it's going to fall maybe let's assume it's going to reach the ground over here. So it's going to fall until it reaches the ground, right? So very important, right? Okay. At what times are the speeds of the ball 0, speed at the maximum, and acceleration 0? Let's see. If you've ever ridden a bike, I'll give this example because it's much easier to understand. If you've ever ridden a bike, this is a bicycle, okay? As the bicycle moves or is being cycled, there will be air resistance, right? There will be air resistance, to be honest, okay? But as the bike moves forward, the air resistance will actually act back. Because if you're riding a bike, the wind is acting as if it's hitting you in the face, right? Because it's actually opposing the motion that you're creating. But come on, guys, if there is no wind hitting your face, there won't be a resultant force. There won't be a resistive force, meaning that there won't be velocity. Because for you to just start to move, the wind will start hitting you up. But if there's no wind, there's no resistive force, then you're not moving because you're stagnant. You can't expect the wind to just hit up on you because you're not moving, right? Air resistance only arises because of motion, right? So at time t, that is where the speed is 0 because you have no resistive force, right? So it would be T1 and T1, so C and D are wrong. But what about the maximum speed? The maximum speed, get this, the maximum speed occurs when the resistive forces are actually equal to the weight. That is where your speed will be very, very maximum. Why? Because as you ride your bike, right, the wind is going to keep on hitting you more and more and more and more. Meaning that as you increase speed, the air resistance is going to increase. If we were to put it on our ball, as our ball falls down, the air resistance will be increasingly acting upwards, right? So as the ball will be falling down, okay, as our ball will be falling down, the air resistance will actually increase, right? So air resistance actually increases, right? So basically that's very important for you to just know that, right? But air resistance and weight will be equal. In a similar way, if you're riding a bike, there is no way. The air resistance, if it's much greater than you, you won't fall. You won't move forward, you move back. Because if the wind comes and just pushes you back, you're going to ride your bike going backwards, right? So in a similar way, if a ball is just falling vertically, it would mean that the air resistance will never be greater than the weight at any particular instant. So meaning that at this moment, where the resistive force is at its maximum, the velocity is also at its maximum. And if the resistive force is now stagnant, it's no longer increasing, it means that the resistive force is equivalent to the weight. And if those two things are equal, you have no acceleration. So your answer is going to be B. Very, 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 very important for you to keep that in mind. Okay. Question number 14. Which diagram best shows the forces acting on a ball falling at a constant velocity through the air? Guys, you need to pay attention to this word, constant velocity. What does it mean? Basically, constant velocity, okay, means one thing and one thing only. It means that there is no acceleration, okay? But I know that F is equivalent to ma, resultant force, that is, right? So if there is no acceleration, it initially means that the resultant force, okay, the resultant force should be equal to 0. If you're on a horizontal plane, right, it means that the force acting backwards and the force acting forwards should be equal, okay? And so basically it means that this force, okay, should be equal, okay, should be equal to that force over there. And the same thing, if you're on a vertical plane, it means that if you have a force acting up, that force must be equal to the force that will be acting down. So essentially, it means that up should be equal to down, okay, should be equal to down, right? So these are the two situations that you need to be paying particular attention to. So if we look at A and B, look at these guys. The upthrust is way bigger because as a ball falls, drag force will act up because it's like air resistance. As it falls down, drag force acts up. But drag force and upthrust combined cannot be more than the weight. That's not constant velocity. That's not equilibrium. It can't be B. The viscous drag and the weight, they cannot be equal alone because upthrust has to act. Whenever you have a liquid, whenever you put something in a liquid, right? So let's assume we're putting a liquid over here, right? Like that. Whenever you put something in a liquid, you need upthrust. It can't happen, right? Then if you look at D, upthrust and viscous drag, they're pretty small, right? And if you're going to combine them, right? So let's remove this upthrust, right? Let me remove this upthrust. And I'm going to combine it and add it up to this thing, right? With the same magnitude in mind. You realize that, oh, sure, this and this, they're now equal. So like this scenario, if up is equal to down, no resultant force. So the answer becomes D. Very important. Move on to question 15. What is the minimum force F that can act? Move on to question 15. What is the minimum force F that can act on each side of the lid in order to open that lid, right? So basically this is a question about torque, right? So torque of a couple, this is a couple. Why is it a couple? Well, torque of a couple is actually going to be one of the force multiplied by the distance between the two forces. So one of the force, the torque already given is 20. One of the force is F. The distance is, here is 4. From here to here, that's also going to be 4. So it's 4 plus 4 divided by 100, right? Divided by 100. So basically that's going to be 8. It's going to be 20 is equivalent to F times 8 over 100. So my value of F will be 20 over 8 over 100. That's going to give me 250 newtons. 250 newtons, the answer is C. Very, very important, right? Okay, move on to the next question. Question 16. Yeah, it looks pretty intimidating from afar, really. But yeah, the diagram shows the brake system of a car. It looks pretty intimidating from afar, really. But let's try it out. The diagram shows the brake system of a car, okay? So, with the force from piston on the brakes, okay, and the force from foot on brake pedal, okay, the pipes are filled with incompressible liquid. What does it mean to say incompressible? You can't compress it. So basically, if you apply pressure here, it's going to be the same. That's going to pressure that's going to move. It's going to be pressure that will be here. That's the pressure that will move. Then will be pressure that will be here. Pressure that will be here. Pressure that will be here. So the pressure, whenever you have incompressible liquid, the pressure is conserved. It's always going to be constant throughout that whole system. Very important to keep that in mind. The area of the piston connected to the brake pedal is 8. So this area, okay, so this here, right here, this is basically 8 cubic, okay, and the area here is 12 cubic centimeters, okay. A force 800 is applied by the foot to the brake pedal. What is the force applied to each brake? So what is the pressure? So the pressure, okay, at pedal, right, is going to be the force at pedal divided by the area of pedal. The force at pedal is 800 divided by the force, which is 8 times 10 to the power of negative 2 squared. You might be confused. How do you convert centimeter squared to meter squared, right? This is how you do it. Centi means 10 to the power of negative 2. That's what centi means. As you can see over there, I've put on the screen all the prefixes that you need for AS. Centi means 10 to the power of negative 2. But this squared also affects this centi, meaning that it would be all of that squared. It could have been millimeter squared. This milli means 10 to the power of negative 3. All of that squared, right? So that's how you basically convert it in a very easy way. So this is 800 over 8 times 10 to the power of negative 2 squared. And that is going to give me 1, 2, 3, 4. That's going to give me this as my pressure at the pedal. But I want to find the force at brake, right? Okay, the force at brake. I know that pressure is equal to force divided by area. So the force will be the pressure multiplied by the area. So it's going to be 1, 2, 1, 2, 1, 2 multiplied by 12 times 10 to the power of negative 2. Remember, squared. That's going to be 1,200 newtons. 1,200 newtons. The answer is C. Very important. Move on to question 17. Okay. We've been asked to find the resultant force. We've given four forces that act at this arm. Okay, so we've given arm PO, O, and that, which are each 1 meter long, and it's pivoted at O. Forces act at the ends of the arms and on the midpoint of the arms. So this is the midpoint, meaning that this is actually 0.5 meters, right? Very important because it's the midpoint, right? Okay, so what is the magnitude of the resultant moment on the structure? So what I want you to keep in mind, bear in mind this, is this aspect of this question. But most importantly, what I'm interested in is this aspect, the resultant moment. How do you find the resultant moment? Okay, so with regards to resultant moment, you need two things. You need to find your anti-clockwise moments. State them down, right? Then you need to find your clockwise moments. State them down, right? Then subtract the two and you get your resultant moment. That's how it works, basically. So in this system, what is clockwise? What is anti-clockwise? Let's go back to the fundamentals. Let's go back to the principles. How does a clock work? A stopwatch, if it's rotating, swiping from 12, 1, 2, 3, that's clockwise, right? So this is clockwise. This is basically clockwise, right? And if a watch is moving in the opposite direction, this is anti-clockwise. So this is anti-clockwise moments, right? So how do I find moment? Moment is basically the force. So moment is actually the force multiplied by the distance from pivot, right? Okay, so that's very important, right? So let's first start. Let's start here. Let's start with the anti-clockwise moments first, moving in that direction, right? So that's anti-clockwise and that's clockwise. Okay, so this is clockwise, right? So no. This is clockwise, right? So if it's anti-clockwise, you're moving in the opposite direction. What does it mean? You're moving in this direction, right? So this is clockwise and this is anti-clockwise. Anti-clockwise movement. If the stopwatch is moving in that direction, that's anti-clockwise. So firstly, here I have a 50 and a 30. So this is going to push with the 50 and this is going to push with the 30. And the 50 is going to win. And as the 50 wins, it's going to win by 20. Okay, so all of these two are going to change, right? This 30 is going to go, it won't be available, and this 50 will change from being a 50 and it's now going to be 20 newtons, right? Is it clockwise or anti-clockwise? It's clockwise, right? So it's going to be 20. Let's first start with that one. 20 times 0.5 plus, let's move on. Let's go into to OS. At OS, again, I have 30 and 20. They're going to fight. 30 is going to win by how much? By 10. Okay, so let's remove it. It's going to say 20, you lose, and 30 is going to change, and it's going to be 10 newtons, right? So it's going to change, and it's going to be 10. Is 10 clockwise or anti-clockwise? It's anti-clockwise, so it's going to be 10 times 0.5 plus 70, clockwise or anti-clockwise? Clockwise. 70 times 1 plus, let's move here. Over here, clockwise or anti-clockwise? That's clockwise. 50. Okay, 50 times that's 0.5. Okay, plus, let's move on to this side. This is anti-clockwise. That is also anti-clockwise. That's 20 times 0.5 plus, that is also anti-clockwise. 70 times 1, right? That's going to give you a total of approximately 155. Okay, Newton meters, and that's going to give you a total of 35 Newton meters. Okay, so the resultant will just be the difference, right? So the resultant will be, okay, anti-clockwise subtract clockwise, which will be 155 subtract 35, which will be 120 Newton meters. 120, which is going to be C. Okay, so the answer is going to be C. Very important. Question 18. On the surface of a planet, 30 joules of work is done against gravity to raise a mass of 1 kg through a height of 10. Okay, so let's first start here. So 30 joules of energy. So we know that gravitational potential energy is going to be mgh. So basically, it's 30. That's going to be the mass is 1 times g times the height, which is 10. So we want to find the value of g basically. So it's going to be 10 divided by 30. 30 divided by 10, which is going to be 3 meters per second squared. So that's the value of g that we have, right? So that's the value of g that we're dealing with, right? So now we go on to the next particular scenario. We have the mass, now we have the height, we just want to find the work. So that's going to be much easier because we already have the value of g. So just go and say GPE is now going to be, my mass is 4, my g is 3, my height is 5. And that's all going to give you 60 joules. So 18 is going to be B. Okay, so I'm going to give you 60 joules and 18 is going to be B. In case you're wondering, they said on a particular planet, the value of G is 3, right? So I don't know specifically the planet that has 3, but the closest to this are Mars and Mercury, right? Mars has a value of G of 3.59 and Mercury has, Mars, so I don't know quite specifically the planet that has a value of G of 3, but the closest ones are Mercury with a value of G of about 3.57, and Mercury is one of the smallest planets, right? Basically, it's one of the smallest planets in our it's one of the smallest planets in our solar system. And Mercury, what's interesting about it, is one of the fastest moving planet in the Milky Way galaxy, right? And Mercury also has, and Mars is the one with about 3.77, one of the hot deserts, right? One of the big planets in the Milky Way galaxy. So, just to give some context, right? It could be one of those two planets. It could be a whole new planet. It doesn't really matter. But you just have to find the value of G there and then find the value of your gravitational potential energy. Very important. Move on to question number 19. The speed of a car increases from 10 to 15, and its kinetic energy increases by E1. Right. Later, the speed of the car increases from 15 to 25, and its kinetic energy increases by E2. What is the ratio of E2 over E1? Let's use numbers, guys. Make up a mass, right? Let's say the mass of this car is 1,000. So in the beginning, right? The mass of that car is 1,000. In the beginning, it's 1/2, right? mv squared, that's your EK, right? And the change in kinetic energy is actually 1/2 your mass multiplied by v squared minus u squared. So it's going to be 1/2. The mass is 1,000. I've just made that up. Times the value of v, which is the final one will be 15 squared. Subtract 10 squared. That's going to give an answer of 62,500 joules. The other one, delta EK for the other scenario, 1/2 times 1,000 multiplied by the value of v is going to be 25 squared minus 15 squared. It's going to give you about 200,000 joules, right? So these are the two E1 and E2s that you've got. This is E2, okay? And this is E1. How do I find the ratio? Pretty simple. The ratio will just be E2 over E1, which is 200,000 divided by 62,500. And that's going to give you an answer of 3.2, which is going to be C. Very important, right? Moving on to question 20. A car travels at a constant speed of 20 meters per second up a slope. The wheels of the car is driven by an engine exerting a force of 30 newtons forward. There's also a drag force and a frictional force of 2,100. The weight of the car has a component down the slope of 900. Let's draw a diagram, guys. So this is our slope, basically. Something like this, right? And we have a car that is on that particular slope, okay? So the weight of the car, the component of the weight is going to be acting downwards, right? So that's 900, right? Work done against frictional forces is also going to be acting down, and that's going to also be 2,100. That's pretty big, 2,100 newtons, right? And the car is just going to push with about 3,000 newtons so that everything is balanced. At which rate is thermal energy being dissipated? So the rate of energy dissipation, that's just power. And we know that power is equivalent to force multiplied by the velocity. The force is 2,100 because the air resistance is the thermal energy that will be there, right? We dissipate thermal energy when we're overcoming resistive forces. So it's going to be 2,100 multiplied by the speed, which is going to be 25. And that's going to give you about 5.3 times 10 to the power of 4, which is about 52,500, right? So that's about 5.3 times 10 to the power of 4, and the answer for 20 is C. Move on to question 21. Which force extension graph shows the plastic deformation of a material line, right? So what is plastic deformation? Plastic deformation basically refers to you've extended an object to a point where if you remove the deforming force, it does not return to its original position. You have a wire or a spring, to be more precise. You put a mass, a very heavy mass to be honest, and the spring is going to be so taut that it won't return back. It has undergone plastic deformation. So it's going to have a permanent extension, which you can see over here. When the force is 0, you have an extension. How is that possible? Because it has undergone plastic deformation. So the answer is going to be D, right? C is basically for rubber, and A is basically for like something that obeys Hooke's law. B is basically for something that obeys Hooke's law, but exceeded the limit of proportionality. But it still returns back, so it's still in the elastic it's still in the elastic region, right? So it still has elastic deformation occurring. It still returns back to its original state, right? Very important. We'll be given 4 solids, steel rods, each of length, right? We're given length, area, we're given equally supporting object of weight, we're given the load. The weight causes the rod to contract by 0.10 meters. What is the Young modulus of the steel? Get this, guys. Young modulus is basically equivalent to the ratio of stress to strain, okay? But stress is basically force divided by area, okay? And strain is basically the extension, okay, per unit length, right? Per unit length, right? So those are the two things that you need to be thinking about. Stress is that, and the extension is that. Okay, so once you've established this, let's get to our question. Okay, so we have 4 solid steel rods. 4 solid steel rods, and as you can see over there, those are our 4 solid steel rods. 1, 2, 3, 4. Right? So those are 4 solid steel rods, and they each support, okay, an object of weight 10,000. So they're each supporting an object of weight 10,000 newtons, right? So it's 10,000 newtons. So if I'm looking at one thing, if 4 of them are supporting 10,000 newtons, what is one thing going to support? It's going to be 2,500. Because if 10 supports 10,000, if 4 supports 10,000, then 1 will support 2,500. So my force is going to be 2,500. My length is 2. My area is 250 times 10 to the power of negative 3 squared. My extension is 0.1 times 10 to the power of negative 3. That's going to give me 2.0 times 10 to the power of 11, which is going to be B. Okay, so very important for you to be thinking of that. First, you were given 4 solid steel objects, so 4 of them are going to evenly distribute their weight, and you then had to look at how you can then find the Young modulus just by plugging in the values that you're given. Very important. 23. High frequency sound with this frequency travels with the speed of that. What is the shortest distance between a compression and a rarefaction in liquid? So basically, that's a compression and that's a rarefaction, right? So we know that V is equals to F lambda, our famous wave equation, right? So our lambda is basically going to be V over F, which is 2 kilometers, is 2 times 10 to the power of 3, divided by 2 times 10 to the power of 6. Mega is times 10 to the power of negative 6. As you can see over there, those are the prefixes that you need to use in AS. And if you compute this, it's basically going to give you a lambda of 1 times 10 to the power of negative 3 meters. But remember, from compression to rarefaction, it's half lambda, which is going to be half times 1 times 10 to the power of negative 3. That's going to give you 0.5 millimeters. So the answer is going to be A. Very important. I'll move on to question 24. A transverse progressive wave of wavelength lambda is set up on a straight string. The graph shows the variation of displacement y with distance x at a particular instant of time. The displacement where x is the lambda over 8 is y1. And what are the next 2 values of x where the displacement y is again equal to y1? So what you're going to do is you're going to draw a horizontal line. Okay? So we're going to draw a horizontal line that's going to cut through here. like that. And where are the points that is equal to y1? The first one, 1 is here. The next one, 1 is there. The next one, 1 is there, 1 is there, and 1 is there, right? So I have 1, 2, 3, 4, 5. I have 5 points where it's now going to be equal to y1, right? So let's first start with the other one because they said the next two values, paying particular attention to the word next, right? So let's first start with that one. Since this is lambda over 2 and this is symmetrical, right? If this is lambda over 2, this is also going to be lambda over 8, sorry. This is also going to be lambda over 8. So the first one, the first value, okay, so the first value is going to be 1/2 minus 1 over 8, which is going to give me 3 over 8, meaning that this is actually 3 over 8. Because if I add 1 over 8, I'm now at 1/2. That's why I said half minus 1 over 8. So my first value is going to be 3 over 8 lambda. It can't be C, it can't be D. The second value is going to be this one, right? 1 after lambda itself, right? So since lambda is going to be 1 lambda, and I'm going to add 1 plus 1 over 8, right? So my second value, okay? So my second is going to be 1 plus 1 over 8. That's simply 9 over 8 lambda, right? So it's 9 over 8 lambda. My answer is B. Very important. Question 25. A man stands next to a stationary train, right? As you can see, that's the man standing next to that train, which is stationary. And he hears a sound of frequency 400 hertz. So that train emits a sound of frequency 400 hertz. The train then moves directly towards the man. As they move right towards the man, basically, with Doppler effect, as you move towards, right, as you move towards observer, okay, move towards the observer, the frequency basically will increase, right? And the Doppler equation is basically F naught is Fs V over V minus Vs, provided that it's moving towards what? Provided that it's moving towards the observer. So that was the golden rule, right? So our initial frequency, 400, right? Multiplied by the value of V, which is 340, divided by 340, subtract 50, is basically going to give you an answer of 348.72 hertz. That's about 349. But get this, guys. The answer is there, which is C. But that is not the correct answer because the question said the difference in frequency. So that's how things work. They will just give you information which is not correct, right? So the difference in frequency is actually now going to be 400 minus 349. That's going to give you an answer of 51 hertz. So the answer is going to be A. Very, very important. Very important. Okay, move on to question 26. We're given a stationary wave that is formed on a stretched string. Okay, so this string is stretched, and the diagram illustrates that string at an instant when the displacement is at its maximum. So displacement is over here, and it is at its maximum. So the frequency of the wave is actually 250 hertz. Okay, so we want to find, we've given that this, at that point, it is a vertical displacement of negative 1.0. So we want to find the vertical displacement of the point P after a time of 5 milliseconds. Okay, so very important. So how is this going to work? Well, if you look at this, the string has actually it has a frequency of 250. So we can find the period. Okay, we can find the period, which is actually, if you think about this, actually 1 over 250, which is 4 times 10 to the power of negative 3 seconds, right? So the period is 4 times 10 to the power of negative seconds. But what does the period really mean, right? If you look at the pendulum, again, I give you the same example. If the pendulum moves to the other side, that is the first cycle. If it moves back, the second. If it moves back, the third. And if it moves to the other side, back to its equilibrium position again, that would be the fourth, right? So basically, that's how pendulums work. If we put it in like stationary waves formation, if you have a point, for example, if you have a point that is like at this point, if you're going to move above, that would be 1, right? That would be, in this case, it would be 1 times 10 to the power of negative 3. If you were to come down, that would be another, that would be 2, right? So it would be 1 times 10 to the power of negative 3 again. If we were to move down from that position, that would be, again, third, 1 times 10 to the power of negative 3. If we were to move up, again, that would be 1 times 10 to the power of negative 3. So whenever we talk of period, we are really talking of 4 motions. Up, come back down. Go down, come back up. Those are 4 motions, right? So let's consider P. The first motion of P will be this, right? So 5 milliseconds means that if I were to say if I were to do this, there'll be 5 motions, right? So the first one, this is my first motion, right? So this is motion number 1. Okay, so motion number 1, right? We go up. Motion number 2, we go up again. That's motion number 2. Motion number 3, we do that. Motion number 4, we're there. And motion number 5, we're back to that equilibrium position. So motion number 5, we'll be back to the position that we started, and point P will be over there. So basically that's how it works. Determine the period and then work with the time that you have to reach a displacement that will be of 0. Very important. Moving to question 27. Observable interference fringes are produced using light from a double slit. The intensity of the light is initially the same. So let's draw our double slit. If we draw a double slit, but let's just use this double slit that is already there, right? So that it's more convenient. So the intensity of light coming from one of the slits. So basically the light is going to do it like this. Okay, so let's assume that we have light coming in, something like that. Then the other light is coming in like that from that other slit, right? So those are the two lights that we have, right? Now we're reducing the intensity of light from one slit, as the question says. The intensity of light from one of the slits is reduced. So we take one slit away and we reduce its intensity. So it's more like that, right? So it was like that. That was its initial intensity. And now it has been reduced to a very lower intensity. How would this affect the interference pattern? Let's look at this. How does interference occur in the first place? We have two kinds of interference. We have constructive. Okay, constructive interference results in bright fringes occurring, right? If you have a wave with amplitude A, okay, and another wave with amplitude A, okay, they'll add up, they'll give you 2A, right? Number 2, it can also be destructive. How does destructive work? This results in formation of dark fringes. If you have a wave with an amplitude of A and another wave with an amplitude of A, those two subtract, they give you an amplitude of 0. But get this, intensity is equivalent to Ka squared, right? So if you're going to reduce this intensity without even using numbers, if you're going to reduce I on this side, you have to agree that A squared is also going to decrease. So the amplitude of light at one of these things is going to change. So if the amplitude is going to change, what this basically means is that its intensity, because it has decreased, the amplitude is going to decrease. Let's assume I had A and A meeting. Now I have A and half A meeting, right? So that's going to form 3 over 2A. This is for the bright fringe. So the bright fringe was once 2A, now it's usually 3 over 2A. It's going to be less bright, right? For the dark fringe, it will be A minus 1/2 of A, which is actually half A. That's going to be your dark fringe. So your dark fringe is now going to have a certain amplitude that's going to reach that bright fringe. So the bright fringe are going to become darker, but the darker fringes are going to become lighter. So the answer becomes D. So very important, right? Whenever you're given these intensity problems, always think, how is the intensity changing? If the intensity is reduced for one of those slits, it means that the intensity for one of those, the amplitude for that is going to decrease. If it's constructive, it won't be full constructive, so it won't be as bright as it once was. It will be darker. If it's destructive, it won't be full destructive. It's going to be lighter than it once was. That's how interference basically works, okay? Move on to question 28. I'm going to give you monochromatic light of this wavelength, okay? So very important, this is the wavelength, and it passes through two parallel slits, which are 0.30 millimeters apart. Bright fringes are observed on a screen 2 meters away. How far are the bright fringes on the screen? So very important. We use the formula, lambda is equivalent to AX divided by D. So lambda is equal to AX divided by D. What are we trying to find in this equation? We're trying to find the value of X. So the value of X is actually lambda times D divided by A. What is our lambda? 450 times 10 to the power of -9. Multiplied by, what is the value of D? 2.0 divided by the value of A, which is 0.30 times 10 to the power of -3. That's going to give us about 3.0 millimeters, right? So 3.0 millimeters, our answer is C. Very important. Question 29. A microwave transmitter is placed at a fixed distance from a flat reflecting surface, okay? So the microwave is moved steadily in a straight line from X to Y. A series of maxima and minima is obtained. So let's draw them, right? So let's draw a series of maxima and minima that we might observe. So it's something like this, right? Okay, so this is basically a series of maxima and minima. And the question is telling us the distance between adjacent maxima. So this is an antinode in maxima, this is another maxima. And the question is telling me that the distance between this maxima and that maxima, this distance is actually, guess this, it's actually 1.5 centimeters. So how do I find my frequency? Guess this, I know that V is equivalent to F lambda, okay? So V for sound waves is 3 times 10 to the power of 8. Electromagnetic waves travel at that speed, right? Meters per second. And my value of lambda, well, you know that from an antinode to an antinode, it's going to be half lambda. From a node to a node, it's going to be half lambda. From a node to an antinode, it's going to be 1/4 of lambda, okay? 1/4 of lambda. From a node, we skip, we go into another node. This is actually lambda, right? But if we have another antinode and we have another node, this is going to be lambda as itself, right? So basically that's how it works. From antinode to antinode, half lambda. From antinode, lambda. Node to node, half lambda, okay? So what we're given here is actually half lambda, right? So half lambda is actually 1.5 centimeters, right? So my value of F will be 3 times 10 to the power of 8, right? So it's 3 times 10 to the power of 8 divided by this times 2, that's 3.0 times 10 to the power of -2. That's going to give me an answer of 1.0 times 10 to the power of 10. 1.0 times 10 to the power of 10, and that is C. Okay, so question 30. This is a question on electric fields. Okay, if you're doing the Cambridge syllabus from 2022 onwards, they've been removed from our syllabus, so we won't be covering them. We won't do number 30. We won't do number 31, and we'll start from number 32, okay? The diagram shows a junction in which a circuit has 3 wires, P, Q, and R, which meets. We've given the currents themselves and how much charge passes through point R in a time of 5 seconds. So you need to apply what we call Kirchoff's, okay? So Kirchoff's first law. Basically, that's what you need to apply. What does it say? The sum of current, okay? The sum of current into a junction, okay, is equal to the sum of current out of a junction, right? So identify a junction. That's the trick with Kirchoff's first law. Identify a junction. This is my junction, right? Identify what's going into the junction and what's going out of the junction. So in this case, this is going out, meaning that this has to come in, because if this come in and that come in, this will go out. So this has to be 2 amps, right? We've identified that in R, the resistance is 2 amps. The current, is 2 amps, right? But I know that Q is actually equivalent to IT. So I have 2 multiplied by 5. That should give me 10 coulombs. So my answer is going to be C. Very important. Moving to question 33. A wire carries a current of 2 amps for 1 hour. How many electrons pass through this point, right? So it's a question with regards to the number of electrons that are going to pass a specific point once you've been given the current and that particular thing. Okay, so we know that Q is equivalent to IT and IT is equivalent to NE. This is golden, guys. This is going to solve any problem that deals with the number of charge carriers that you're going to talk with, right? Right, and you're particularly interested in this part of this equation, right? Because this is where I have current, I have time, I have the value of E, right? So I just want to find the value of N, right? So I know that N will be equivalent to 2.0 times 3,600 divided by my value of E, which is 1.6, which is 1.6, okay, times 10 to the power of -19. That's going to give me 4.5, okay? It's going to give me 4.5 times 10 to the power of 22, right? So the answer is going to be D. Right? So it's very important for you to just think of that equation and just apply it whenever they ask number of particles, whenever they ask for current. Using those equations which relates Q, IT, and NE, you can actually find anything that you want. NE meaning the number of charge carriers. So if you have 1 million charge carriers times E, that is the total charge that is there. I is current and T is time. Okay, so this is charge. This is current. Okay, that is time. And that is number of charge carriers. And the value of E is actually 1.6 times 10 to the power of negative 19. Very important. Moving to question 34. The diagram shows an electric circuit in which the resistance of the external resistor is 2R and the internal resistor is R, right? What is the ratio of power in the internal resistance over power in the external resistance? So for question 34, you basically need to know what power is. So power in electricity can be expressed as the product of voltage multiplied by the current, right? So that's the definition for the product of power itself. But we know that V is equivalent to IR. So power will be IR multiplied by the value of R, which is going to be I squared R, okay? So if I want to find the ratio of power in internal resistance of that, I'm going to just say, okay, if I go here, I'm going to say I squared multiplied by R divided by I squared multiplied by 2R. Okay, so this will cancel out, that will cancel out, and I'll be left with 1/2. Okay, and my answer is going to be B. Very important. Moving to question 35. The graph shows the variation with potential difference of current I in components X, Y, and Z, which correctly identifies these components. As you can see on your right, those are the components that you need to know. You need to know the semiconductor diode. You need to know the metallic conductor. You need to know the filament lamp. So basically, this graph, guys, this is the graph of a diode, right? And this is the graph of a metallic conductor. And this is the graph of a filament lamp. Okay, so this graph specifically is the graph of a filament lamp, and that graph is a diode. And this graph, okay, that graph is the graph of a metallic conductor. So those are the three graphs that you need to be thinking about, right? So X, so the metallic conductor is Y, so the metallic conductor is YY, okay? The semiconductor diode is X, okay, X. So the answer will be B. So 35, the answer is B. Very important. Moving to question 36. So 35, the question is B. The 35, the answer is B. Question 36. 4 statements about either potential difference or electromotive force are listed. What is potential difference? Well, potential difference is the energy per unit charge, right? So it's the work done per unit charge, but moving it from one point to another. So that is potential difference. I give an example. You have a cell, okay? And this is your load, right? So like this. As electrons get out of the battery, they're given a bunch of energy. And they're going to work with that energy across the whole cell. But electrons have a rule. They will deposit all of their energy into a component. So if they're moving from this point, right? So if they're moving from this point to that point, they're going to deposit all their energy. So if they had a lot of energy here, after this, they're going to have no energy. They go back to the cell, they get a refill. But if they are at the cell, they'll get chemical energy transferred into electrical energy. So that is EMF, right? The energy changed, right? So for EMF, it's basically changing other forms of energy into electrical energy, right? And it is now for that charge to move around a complete circuit, right? So EMF is for that charge to move across a complete circuit. So it has to be 2 and 3. That's for EMF, 2 and 3. And for potential difference, well, potential difference is going to be pretty simple. So potential difference is going to be the energy converted from electrical into other forms, and it's going to be the work done per unit charge from maybe from this point up until that point. So it's going to be 1 and 4, which is going to be B. Very important. In this question, we've been given question number 37. In the circuit shown, there is a current of 3 amps in the 2 ohm resistor. What are the values of current I delivered by the power and the voltage V that is across it? Okay, so let's look at this. We've been given a current of 3 amps in the 2 ohm resistor. Okay, so this is 3M and this is that particular resistor. Okay, so what can we do, right? We basically find the potential difference across this component, right? Once we find it, it's going to be the same as the potential difference that will be in that component itself, right? So how do you find the potential difference across that component? We know that V is actually equivalent to IR, okay, right? So the value of V is really going to be 2.0 multiplied by 3.0, right? So 2.0 multiplied by 3.0, that's going to give you 6 volts, right? So basically over here, there's going to be 6 volts, meaning here, since they're in parallel, as electrons are here, they're going to make a decision. Should they move down or should they move up, right? So if they move up, because it is a lower resistance, more electrons will move there. That's why you have a higher current, which is over there. But the energy is going to be the same. Those electrons contain the same energy, but they just decided to go in different routes. Others decided to go down here. Others decided to go up here, right? They have two different routes, but they're still the exact same electrons, right? Which is very important for us to be able to work on that one, right? So since that is 6 volts, I can therefore find the current, right? I can therefore find the current delivered, which is over there, because I can find the current in the 6 ohm resistor, and I can apply Kirchoff's first law, right? So the current, okay, so the current in the 6 ohm resistor, okay, in the 6 ohm resistor will therefore be, what is the voltage over across it? 6 divided by 6 will be 1 M, right? Meaning this is 1 M. But if current is going to reach a junction, it's going to spread out. One goes up, one goes down. Meaning before, it was actually 4, right? For it to split one up, one down, it has to be 4. So that it's 3 there and 1 there. So it has to be 4 over there. And I want to find the power supply and the voltage across it, right? So basically, since there's a current of 3 ohms in the 2 ohm resistor, we want to find this particular value of V, which is across the total V that is there, right? But for that scenario, so for case 2, okay, this was for case 1, okay, so for case 2, we now know that V will be equivalent to I multiplied by R total, okay? So what is the value of R total? That is what we need to find. So once you have the value of R total, we can therefore be able to find, we can therefore be able to find the value of V, right? So R total is basically going to be, those two which are in parallel is 2 times 6 divided by 2 plus 6, right? And we're going to add the one that is in series, which is 1.5. That's going to give us a total of, so it's of 3, right? So it's going to give us a total of 3 ohms, right? So it's going to be 3 ohms that is flowing across the whole circuit, right? And I know that V is actually equivalent to IR. So since I have 4 ohms multiplied by 3, that's going to give me 12 volts. So it's going to be 12 volts. 4 and 12, the answer is going to be C. Very important. Move on to question 38. In the circuit below, P is a potentiometer of total resistance 10, and Q is a fixed resistor of resistance 10 also. The battery has an EMF of 4 volts. The slide on the potentiometer is moved from X to Y, and the graph of potential of voltmeter reading V is plotted against the slider position. Which graph can be obtained? My advice is go to 2 points and you'll be done. Go to the point of X and the point of Y. Point of X, point of Y, point of X, point of Y, point of X, point of Y. Determine if the slider is at X, what V do you get? What is the value of V that you're getting here, right? And once you've determined that value, right, what value do you get over here? You can therefore be able to say, if I have this particular voltage over there when it's at X, it can't be B, it can be A. You can then eliminate once you have that particular fact, right? So let's start by positioning it at X, right? So let's delete it over here, right? Let's delete our slider, okay, and put our slider at X. So we're going to take our slider and we're going to put it at position X. But potential difference is divided based on the voltage that you have. But potential difference is based on the resistance that you have. It's the criterion. The bigger the resistance that you have, the bigger the potential difference that you get, right? So if you're considering this question, now I have 10 and 10. This is the whole circuit. So if electrons are going to come here they're going to have 4 volts when they're at this point, but in the live they're going to have 0 volts. Meaning the potential difference, which is going to be measured here, is actually going to be 4 volts. So we're going to measure a potential difference of 4 volts. So it's going to start at 4, right? Let's start at 4. Let's start at 4. So it can't be B and it can't be D. We're left with A and C. We're going to now switch our positions and we're going to move it, right? We're going to move it to position Y, right? So we're going to, let's move it down and let it be connected at point Y, right? So it's over here. When it's now at point Y, you can see now that there's a 10 ohm resistor that is just connected over there. It will just get that 10 volt. So it will be 10 over 10 plus 10 multiplied by 4, right? So we're saying 10 over 20 multiplied by 4, which is basically half of 4, which is 2, right? So 10 pi plus 10 divided by 4, right? That's basically going to be 2 volts. Meaning at this point, you have 2 volts. At that, you have 0. Meaning your value of V will actually be 2. So at Y, it's going to be 2. It's not going to go down, and it's not going down to reach 0. It's just going to be, answer is 2. So it's not going to go up, it's not going to go down, it's just going to go down. So the answer will be 2. Because it can't go back to 0, from our calculation at y, we still have a potential difference. So it needs to be at 2. And the answer has to be A. So it's very important for you to be thinking of that. What are you given in the question? And how do you use what you're given to come up with a valid conclusion? Okay. Move on to question 39. The calcium nuclide, okay, 42 and 20 is formed by beta negative decay. What are the nucleon mass and proton number of the unstable nuclei that underwent beta minus decay to form the calcium nuclide? So now we're working in reverse. I'm already given 42 and 20 of calcium, and I've been told that it has already undergone beta negative decay, right? Beta negative meaning it emits an electron anti-neutrino. So if we're considering this nuclide S, if we add this, an electron anti-neutrino is 0, 0, right? So it's going to be 42 plus 0, which is going to be 42, okay? Then it's going to be 20 minus 1, which is going to be 19. So it's going to be 19 over there, and it's going to be 42 over there. So the answer is going to be C, right? Very important for you to be thinking of that. Which diagram represents the structure of an anti-neutron? So antimatter is basically the same as matter, but just has opposite, okay? It just has opposite charges. The same as matter, what's different is just the charge. So how do you go about this? Let's draw the neutron first, okay? So basically a neutron consists of, okay, a down quark, and an up quark. So it's basically this, right? This is basically a neutron, so it can't be C, because we want to find an anti-neutron. So we just go, if you have a down quark, you want an anti-down quark. If you have a down quark, you also want another anti-down quark. Okay, so the answer is going to be A. We have all of that being antimatter. It can't be B, it can't be D, because this is a proton, okay, which is 2 up quarks and 1 down quark, and this is an anti-proton, which is 2 anti-up quarks and 1 anti-down quark. Very important. So this is the end of my paper. I hope you enjoyed it, and if you just want to look at some of these things, right, I'll be posting the paper down in the description below, so you can access it and be able to download the paper, even look at some of the questions, how we're working them out, and get a rough idea of how you can do this. Thank you for watching. I'll see you in the next one.